What's up, everyone? This is LeetCode 338, counting bits. So we've done this problem in Python. Now we're going to do it in C++. So we're given an integer n as an input, right? And we have to return an array answer of length n plus 1 such that for each I from 0 up to and including n, 0 at I is the number of ones in the binary representation of I, right? So basically from 0 up to and including n, right? We need to basically account for the number of ones in each of those digits. So for example, when n is equal to 2, right, we go from 0, 1, 2, right? That's 0 up to and including n, right? So 0, 1, 2, right? So how many ones in the binary representation does 0 have? Well, 0 has 0 ones. How many ones in the binary representation does 1 have? That'd be 1, right? Because 0, 0, 0, 1, right? There's 1, 1. What about the number 2, right? That has 1 in the binary representation because 2 in binary representation is 0, 0, 1, 0, right? So basically from 0 up to n, right? For that specific I, as we go along, how many ones does that have? And basically we need to put that in an array and basically return the list or the array as an output, right? That's what this question is asking. Kind of hard to explain, but like obviously if you follow the examples it makes more sense. But yeah, so I'm going to draw this out in a comment just to kind of show you what we're doing. So let's pay attention to the power of 2's, right? What do we notice? Well, we notice that for every power of 2, right, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, etc., we're left shifting by 1, right? Notice that? Right? Every power of 2, we're left shifting by 1. So we're going to use this to basically calculate some specific number, how many ones are in it, by using information that we know previously. So it's really like a DP solution, and the kind of formula is a little bit hard to come up with on your own, but it makes sense once it's explained, okay? So really the formula is 1 plus the array of x. X is the digit of the number that we're on, right? So when we go, we have an array, right? A DP array, and so for so we're gonna go 1, we're gonna add 1, and then we're gonna basically go in the array. And where do we go in the array? We're basically gonna go x minus the digit where the power of 2 we're on starts. So for example, let's say we're on digit 11, okay? And we want to find out how many, how do we get this, right? How do we get this? Okay, the way we're going to do that is basically we're going to do, we're going to go array x is 11, right? Minus the digit where the power of 2 we're on starts. Well, the power of 2 that we're currently on is 2 to the power of 3. The digit where that starts is 8, right? So we would do 11 minus 8, right? That would be 3, right? That'd be 3. So we're going to go basically array of 3. So we're going to go array of 3, which is 0, 0, 1, 1. And when we add 1 to that, right, we basically put it on the leftmost place. If it's a 0, we just replace it with 1. If it's a 1, obviously we just add 1 to the left. So basically we have 0, 0. At array of 3, we have 0, 0, 1, 1. And we add 1 to that, so we're going to get 1, 0, 1, 1. Now let's go to the array of 11, right? And we have, again, like I said, 1, 0, 1, 1. It's interesting, right? So you can use the patterns from previous, from basically the previous point in the binary representation of the numbers that came before it to calculate the current one we're on, right? So I'll give you another example. X is equal to 10, right? We're basically going to do, or we can just do 9 first, right? So for x is equal to 9, we want to find out, let's say we don't know what this binary representation is, right? So how do we find the number of ones in it? Okay, we're going to say for x is equal to 9, right? We would do 9 minus, and the power that we're on is 2 to the power of 3. That's the current section that we're on, essentially, right? That's the last power of 3 that we ran into, the last power of 2 that we ran into. So for when x is equal to 9, we basically go, what power of 3, what power of 2 are we on? 3, but the actual digit where that occurs is 8. So we would do 9 minus 8, and we would get 1. So, right, so we would go 1 plus the array of 1. So let's go to the array of 1. We get 0, 0, 0, 1. And we add 1 to that, right? Like I said, if the leftmost bit is a 0, we just replace it with 1. So in this case, we should get 1, 0, 0, 1. Okay? And we get 1, 0, 0, 1, like I said, right? Interesting. Now let's do it for another number, 10. So obviously, 10 is right here. The last power of 2 we saw is at digit 8, so we do 10 minus 8, and we get array 2. Let's go to array 2. 0, 0, 1, 0. When we add 1 to that, we should get 1, 0, 1, 0, right? So when we go to s is equal to 10, we get 1, 0, 1, 0. Interesting. Now let's try for x is equal to 15, right? We have 1, 1, 1, 1, right? Well, we don't know that this is what we're looking for initially. So when x is equal to 15, what would we do? We're at 2 to the power of 3. That's the last power we saw. It occurs at digit 8. So 15 minus 8 is 7. Let's go to array of 7. 0, 1, 1, 1. Okay, when we add 1 to that, we should get all 1s. And for x is equal to 15, we get all 1s. Interesting. Okay. One final one, let's just do 13. So we would do 1, 1, or this is what we should get. We should get 1, 1, 0, 1. Now let's see if that's actually what we get with our formula, okay? So we would do 1 plus array 13 minus 8, and we do minus 8 again because the power of 2 that we're on occurred at digit 8. That's where it was last seen, right? So we would do 13 minus 8, and we get array of 5, right? So we go to the 5th index, and we get 0, 1, 0, 1. Okay, so let's add 1 to that, and we should get 1, 1, 0, 1. What was that? 13? 1, 1, 0, 1. That is what we get. Okay. Now this this obviously works beyond just the digit of 15, but obviously I'm just trying to show you a smaller section or a small subset of examples, because you can really just keep going on and on, obviously. But this is basically the formula, right here. Okay. So how would we code this up? Okay, this is where it gets interesting. Well, first of all, if we're going to have to say this, okay? If n is equal to 0, just return 0, right? Because 0 up to and including 0 is obviously, there is no 1s that you can return, right? Because the binary representation of 0 is 0. There is no 1. There is no 1s in that binary representation, okay? Now we're gonna have to return a array, right? So we'll just make a vector and we'll call it dp of n plus 1, right? And do 0 right here. So what we're doing here is we're making a dp array of n plus 1 because, again, we need to include the index 0 as well. So because we need to include the index 0 and then all the digits up to and including n, right? For example, if n is equal to 2, we need to include the index, we need to include the index 0, the index 1, the index 2, right? So we need n plus 1. We need our array to be n plus 1 in terms of length. By the way, it tells you that up here anyways to kind of help you. And of course, we're going to set all of those initially to 0 because we don't know. We're going to just replace them as we go on, but initially they're all just going to be 0. Okay. Seems easy enough so far, right? So let's create. So we created dp, okay? So dp at 0 should be 0, right? That makes sense because, well, there should be 0 1s at the digit 0. So dp of 0 is already set to 0, right? Because technically we set all of these equal to 0 initially. Well, that's what we should get for 0, but for 1, we shouldn't get that. For 1, it should be 1. So we're just initializing our basically early cases, okay? Now let's calculate for any digit past 1, okay? You know, if n is equal to some other number, how do we calculate this? Okay, so we're going to basically make a variable and call it the next power of 2 and set that to 2, and then the previous power of 2, set that to 1. Okay, because we set this right initially, so this would be not what we care about. this would be what would care about, because this is where we're starting, okay? When we're doing from 0 up to and including n, we handled index 0 and index 1, right? So we're going to do basically we're going to start from 2 up to and including n, okay? And so because we're doing that, let me write this first. Because we're doing that, right, we handled index 0 and index 1, so we're going to start here, right? So this is the previous power of 2, right, as we go along, because we're starting here. So the next power of 2, which is what we're setting here, which is 2, right? The next power of 2 is going to be 2, right? This is basically what's going to tell us when should we change the previous power of 2, because the previous power of 2 is what we use to basically do x minus whatever, right? So that's what it's for, okay? Right? So we're going to go to this. When we're at this 3, for example, we're going to look at the previous power of 2, which is going to be 1. So we're going to go to here, okay? We're going to do 3 minus 1, which should give us 2, right? And we'll go here, right? So I'll show you what this looks like. We're going to say previous, or no, we need a condition first. So we're going to say, okay, if I is equal to the next power of 2, that's where we need to switch stuff, okay? Because at that point, the previous power of 2 is currently the next power of 2, and the next power of 2 is going to be set by doing next power of 2 and just left shifting it by 1, okay? Otherwise, right, otherwise the dp at I is going to be set to 1 plus dp of I minus the previous power of 2, okay? So let's say n is equal to 3, for example, right? Right, let's say n is equal to, let's say we have an input like this, okay? Well, initially we set in the dp array, right? We set dp of 0, right? We set that to 0. We set dp of 1. We set that to 1, right? Which makes sense because when I is equal to 0, right? We should get 0 because that's the binary representation, okay? Right? When I is equal to 1, we should get 1 because this is the binary representation, okay? Now, we're going to start at dp2, obviously, right? We don't know what this is going to be, so let's follow let's follow our algorithm. Okay. So, and let me just keep track of these variables. So, this is what these two are initially, right? This is what these two variables are initially, right? So dp of 2. This is what we need to calculate. Okay. So is I, and let me set what the current I that we're on. We're currently on I is equal to 2. Okay. Is I equal to next power of 2? Yes, it is, right? Because initially we filled this out, right? The next power of 2 is 2. And we're currently at the digit 2, which is the next power of 2, which we initially set up here. So let's change this. So we're going to say, we're going to go previous power of 2 is equal to the next power of 2. Previous power of 2 is 1, right? And maybe I'll just put this up here. So the previous power of 2 is going to be 2, right? Because when we're going at this, look at this digit 2 or this digit 3, the previous power of 2 we encountered should be right here. Okay, that's why we're setting previous power of 2 to 2. Next power of 2, we're just going to bit shift it to the left, right? So we should get 4, right? Right? When we have 2, we bit shift it to the left, we should get 2 to the power of 2, right? So which is 4. Okay. Okay, so we're gonna say dp of what? dp of 2 is equal to 1 plus, right? dp of 2 minus, what's the previous power of 2? It should be 2, right? So we're gonna basically say 1 plus the dp of 0 is going to be 1 plus 0, right? 1 plus 0, right, should give us 1, right? Which makes sense because so this should give us 1, which makes sense, right? Because I, when is equal to 2, right, the binary representation of that is 0, 0, 1, 0. There's only 1, 1, right? Now let's do dp of 3. Okay. Let's do dp of 3 using our algorithm. Okay. Is I equal to the next power of 2? No, it is not. Let's just skip that if statement. So dp at 3 is going to be equal to 1 plus dp of 3 minus, what is the previous power of 2? 2, okay? So that's going to be dp, that's basically saying dp of 1, right? And that's going to be what? 1 plus dp of 1 is 1, right? So that should give us 2, right? Should we get 2? Yes, we should get 2 because this is what the binary representation of 3 looks like. 0, 0, 1, 1, okay? So basically that's the algorithm, okay? I know it's a little bit confusing to wrap your head around the first time, because we're working with integers really, but we're basically keeping track of the binary representation by basically using the patterns of how the digits look when we bit shift them, as well as basically doing current digit we're on minus the last power of 2 we saw, right? And we're basically using previous things that we already calculated to find how many ones are in the current digit that we're looking at, okay? Kind of a long video, I'm sorry. I know this video is extra long, but like I just want to over explain stuff so you kind of understand what we're doing with this algorithm. Yeah. By the way, the person who helped me with this problem, I think, is somebody on YouTube named LeetCoding with Sam or something. I don't remember if that's his exact channel name, but I think he's a senior software engineer at Amazon. He has a great channel, so I suggest you look him up. He helped me understand this problem a lot. I really did not understand the efficient solution to this problem, but he drew out this table like this, and it really, really does help understanding what the pattern is, right? And how we're using previous things in the array that we already calculated to calculate the current number of ones in the current digit, okay? So this is how you do it, right? And of course, obviously, at the end of this, we need to return our dp array. Okay, we're going to run this. We're going to submit. And we have it. Okay. I know this was a long video. I apologize, but I think this is one of those problems that's worth basically going into detail and explanation, just because it can be really confusing if you gloss over little details. But I hope this helped. And yeah, I'll see you in the next one.